So chapter 5 is getting a little bit away from chemistry, it seems, at the beginning when we talk about using equations, because we've typically just been using balanced chemical equations and doing stoichiometry. But when we learn about gases, we can understand the properties of gases using one equation, and that's PV equals nRT. And that reminds us that all of the information about gases basically gets summed up in its pressure, the volume, the temperature that the gas is at, and the quantity of gas that we have. So we started this learning unit by kind of thinking about what it means to be a gas, and we kind of acted out and role-played what it meant to be a gas, comparing gases and liquids and solids. And that kind of comparison is going to be something we'll carry as a thread throughout some other learning units throughout this entire course. But at the end of the day, we learned about using PV equals nRT. And we actually had two different ways that we thought of using that. The first is using it as an equation where there's one unknown that we're solving for, and we called that an unknown variable problem. The second way that we're going to use that equation is by realizing that since all gases can be described by those four properties of pressure, volume, temperature, and quantity, if we change one of those quantities, we can have initial, or number one, conditions, and then final, or number two, conditions. And we can set those equal to one another and then still solve for one variable, but we call those problems changing variable problems. So we spent a good bit of time kind of talking about the differences between those, how to tell when you have one problem versus the other. And then we kind of manipulated PV equals nRT, realizing that we could use it to think about molar mass of gas, and then also thinking about the density of gas. So lots of flavors of different problems that all basically stem from thinking about the pressure, volume, temperature, and quantity relationships of any gas. So I can't highlight this point enough, but make sure when you're doing these types of calculations and using that equation that you only use it with gases. There might be one substance that's in a chemical equation that's a gas, but we're talking about moles of something else. You have to make sure that you're talking about moles of gas in order to use PV equals nRT. So after we learned how to use that equation, it's important to realize that that N stands for moles, and so PV equals nRT just represents another way to walk to moles, which means we can do stoichiometry calculations. So we can do regular old stoichiometry calculations, limiting reactant stoichiometry calculations. So everything that we learned in chapter 3 with stoichiometry kind of gets opened up a little bit as we begin to think about using just another way to get to moles. And so we had sort of that mole map, if you will, that mole game that just became so much bigger because now we know so many different ways to get to moles. Interconverting moles and grams through molecular weight, moles and number of items with Avogadro's number, changing who we're talking about with balanced chemical equations, changing the ratio of atoms or parts within a formula unit using the mole ratio that we have in formulas. And so there's lots of different ways. Molarity is another one. Lots of different ways that we've learned to talk about moles, and PV equals nRT is just another way to get there. So at the very end of the chapter, there's a very qualitative sort of examination of the reality versus ideality. So we call PV equals nRT the ideal gas law because really what's happening there is we're thinking about gases behaving ideally, meaning they take up an infinitely small volume compared to the volume of the container that they're in, that they really don't realize that they have neighbors, and so there's really no interaction between gas particles. And so that allows us to make some simplifying assumptions and use this very simple equation. We're not going to go into any of the details. If you really love this kind of thing, physical chemistry is kind of a home for that type of a thought process. But kinetic molecular theory is sort of the last learning part of this learning unit, but we're really not going to touch too deeply on it. But it helps us think about how we deviate from this ideality and get more reality when we have high pressure and high temperature, because when we squeeze molecules together, now they do start to feel like they have neighbors, and when we make them move faster by increasing temperature, they interact with their neighbors more frequently. So really not a lot of calculations to do with that, purely qualitative, but again that stems back to thinking about the relationships that pressure and temperature have on kind of gas behaviors.